60 seconds. That's how fast Mars turns your dream into your nightmare. Your suit fails, the ground itself turns poisonous. And that's just day one. Invisible radiation, temperatures that swing 200 degrees, an atmosphere that's basically a vacuum. This isn't a planet, it's a killbox wrapped in red dust and social media hype. And here is a question: if you actually had to live on Mars for 1 year, what's the one thing you think would keep you sane? Comment down below. I will pin the most creative answer. Now let's begin. The average temperature on Mars is around -80 degrees Fahrenheit. That's -63 degrees Celsius. But averages don't tell the whole story. At the Martian poles during winter, temperatures can plunge to -143 degrees Celsius. That's colder than dry ice. But here's what makes Martian temperatures particularly treacherous: the dramatic swings. Because the atmosphere is so thin, it can't hold heat. So while a spot on the equator might reach a relatively balmy 70 degrees Fahrenheit, around 20 degrees Celsius, during a summer afternoon, that same spot could drop to -100 degrees Fahrenheit just after sunset. That's a temperature swing of 170 degrees in just a few hours. If you're wondering why this matters, imagine your habitat having to withstand those kinds of thermal stresses every single day. Materials expand when heated and contract when cooled. These constant extreme fluctuations would cause metal fatigue, crack seals, and potentially compromise the structural integrity of anything you build. It's not just about keeping warm, it's about preventing your entire shelter from literally tearing itself apart. Speaking of things tearing apart, we need to talk about dust storms. You've probably seen movies where characters face dramatic Martian storms with winds that threaten to blow everything away. The reality is actually both less and more terrifying than Hollywood depicts. Let me explain. Martian winds can reach speeds of up to 60 miles per hour during regular storms, and during global dust events, they can exceed 100 miles per hour. Sounds intense, right? But here's the twist. Because the atmosphere is so thin, these high-speed winds don't pack the punch you might expect. The force you'd feel from a 100-mile-per-hour wind on Mars would be more like a 20-mile-per-hour breeze on Earth. So, the good news is that winds won't knock over your habitat like they showed in the Martian movie. The bad news: the dust itself is the real villain here. Martian dust is incredibly fine, much finer than sand, more like talcum powder. It gets into everything, and I mean everything. It would coat solar panels, reducing power generation. It would clog mechanical systems. It would infiltrate habitats, despite your best efforts to seal them. And this isn't ordinary dust. If you're finding this journey through Mars fascinating and terrifying at the same time, please hit that subscribe button and give this video a thumbs up. Your support helps me continue bringing you deep dives into the wonders of our universe. Martian dust particles are sharp and jagged, almost like tiny shards of glass. They're also electrostatically charged, which means they cling to surfaces with surprising tenacity. Astronauts on the Apollo missions to the Moon dealt with similar dust, and they reported that it was one of their biggest operational headaches. The lunar dust got into their suits, irritated their eyes and lungs, and damaged equipment. Martian dust would be even worse because dust storms on Mars can last for weeks or even months. In fact, in 2018, Mars experienced what scientists call a planet-encircling dust storm, also called a global dust storm. These massive events happen roughly once every 3 to 4 Martian years. The storm that year covered the entire planet, blocking out the sun and plunging the surface into darkness. NASA's Opportunity rover, which had been exploring Mars since 2004, was caught in this storm. The dust was so thick that its solar panels couldn't generate power. Opportunity sent its last transmission on June 10, 2018, and was never heard from again. Imagine being on Mars when one of these storms hits. The sky darkens, Temperatures drop even further because sunlight can't reach the surface. If you're relying on solar power, your energy reserves start draining. You're trapped inside your habitat, watching your life support systems slowly deplete, hoping the storm clears before your resources run out. It's a nightmare scenario that's not a matter of if, but when. And yet, despite all these horrors, there's something even more insidious lurking in the Martian soil: perchlorates. These are chemical compounds containing chlorine that are found abundantly across the Martian surface. NASA's Phoenix lander discovered them back in 2008, and subsequent missions have confirmed they're pretty much everywhere. Perchlorates are toxic to humans. They interfere with thyroid function and can cause serious health problems even in small amounts. But on Mars, they're not in small amounts. They make up about 0.5% of the soil by weight in many locations. That means any dust that gets into your habitat, any soil you might want to use for growing food, is contaminated with these chemicals. You can't just wash them away easily either, because they're water-soluble and would contaminate any water recycling systems. The presence of perchlorates creates a cascading series of problems that engineers and scientists are still trying to solve. If you want to grow food on Mars, which is essential for long-term survival, you can't just dig up Martian soil and plant seeds. You'd need to either completely remove the perchlorates through complex chemical processes, or bring all your soil from Earth, which would cost millions of dollars per kilogram to transport. Neither option is particularly appealing when you're trying to establish a self-sustaining colony. But let's say you've somehow managed to deal with the perchlorates. You've scrubbed your soil, you've sealed your habitat against dust, you've shielded yourself from radiation, and you've created a pressurized environment with breathable air. Congratulations, you're still not safe, because Mars has another trick up its sleeve: regolith toxicity beyond just perchlorates. Recent studies analyzing data from NASA's Curiosity rover have revealed that Martian soil contains a cocktail of potentially harmful substances. There are heavy metals like chromium, arsenic, and lead. There are sulfates and chlorides in concentrations that would cause problems for both humans and any plants you'd try to grow. Some researchers have even suggested that the soil might be directly toxic to bacteria, which would make composting and biological waste processing incredibly difficult. Think about what this means for a moment. On Earth, soil is alive. It's teeming with microorganisms, insects, fungi, all working together to break down organic matter and make nutrients available to plants. Martian soil is sterile and hostile. You'd essentially have to create an entire ecosystem from scratch, protected from the native environment, using resources that are scarce and precious. Every mistake could be catastrophic. Now, let's discuss water, because surely if there's water on Mars, that solves a lot of problems, right? Well, yes and no. We know Mars has water. NASA's Mars Reconnaissance Orbiter has detected vast deposits of subsurface ice, particularly at higher latitudes. The Phoenix lander even dug up water ice in 2008. More recently, the InSight lander and other missions have provided data suggesting that liquid water might exist deep underground in certain regions. But here's the catch: accessing that water is extraordinarily difficult. The surface ice is buried beneath layers of soil and rock. You'd need to dig, and digging on Mars means dealing with all those toxic compounds we just discussed. You'd need power-hungry equipment. You'd need to protect that equipment from the extreme cold and dust. And once you've extracted the ice, you need to melt it and purify it, processes that require significant energy when the temperature is 100 degrees below zero. Furthermore, any liquid water you manage to create would instantly try to evaporate or freeze because of the low atmospheric pressure and frigid temperatures. You'd need to keep it in sealed, heated containers at all times. A spill wouldn't just be inconvenient, It would be a major loss of one of your most critical resources. Water is heavy, so bringing large quantities from Earth is impractical. That means every drop of water on Mars is precious beyond measure. Speaking of resources, let's talk about energy. How do you power a habitat on a world where every system needs to run continuously to keep you alive? Solar panels seem like an obvious choice. Mars gets sunlight after all, and several missions have successfully used solar power there. But Martian solar panels face significant challenges. First, Mars is about 50% farther from the Sun than Earth is, which means solar panels receive only about 43% of the sunlight they would get here. That's less than half the power right off the bat. Second, those dust storms we talked about. They coat solar panels, drastically reducing their efficiency. The Opportunity rover lasted as long as it did partly because Martian winds occasionally cleaned its panels. But you can't count on that happening when you need it most. During a global dust storm, solar panels might generate only 5 to 10% of their normal output, or potentially nothing at all if the dust is thick enough. If that storm lasts for months, as the 2018 storm did, you'd better have some serious battery backup or an alternative power source. Nuclear power is another option. NASA's Curiosity rover and the Perseverance rover both use radioisotope thermoelectric generators, or RTGs, which convert heat from radioactive decay into electricity. These are reliable and work regardless of dust storms or time of day. However, they're expensive, heavily regulated, and produce relatively small amounts of power compared to what a human habitat would need. A crewed mission would likely require larger nuclear reactors, which bring their own challenges in terms of safety, cooling, and maintenance in such a harsh environment. And here's something that doesn't get discussed enough: the psychological impact of living on Mars. This isn't just about physical survival. It's about mental survival in an environment that's fundamentally alien and hostile. You'd be living in a small, confined space with a handful of other people, knowing that outside those walls is a planet trying to kill you every second of every day. Earth would be a distant point of light in the sky. Communication with home would have a time delay of anywhere from 4 to 24 minutes, depending on where Earth and Mars are in their orbits. You couldn't have a real conversation. You couldn't call for help in an emergency. If something goes wrong, you and your crew are on your own. That level of isolation, combined with the constant stress of living in a life-threatening environment, would take a severe psychological toll. Studies conducted in Mars analog habitats here on Earth, like the HIC project in Hawaii and simulations in Antarctica, have shown that even with careful crew selection and psychological support, people experience depression, anxiety, interpersonal conflicts, and cognitive decline over long-duration missions. Now imagine adding actual mortal danger and the knowledge that there's no real escape. Some researchers believe that the psychological challenges of Mars colonization might actually be harder to overcome than the technical ones. But wait, there's another aspect of Mars that we haven't fully explored yet: the planet's geology and its implications for safety. Mars is geologically active, though not in the same way Earth is. It doesn't have plate tectonics, so you don't have to worry about earthquakes in the traditional sense. However, NASA's InSight lander, which operated from 2018 until late 2022, detected thousands of Marsquakes during its mission. These Marsquakes were caused by the gradual cooling and contraction of the planet's interior, as well as by stress from the Tharsis volcanic region. While most of these quakes were relatively small, measuring below magnitude 5, they still represent a hazard. A habitat on Mars would need to be engineered to withstand seismic activity, adding another layer of complexity to construction. If you're fascinated by all the obstacles standing between humanity and Mars colonization, I actually created an entire video exploring this topic in much greater depth. It's called "What is Actually Preventing Us from Colonizing Mars?", where I break down not just the environmental challenges we're discussing today, but also the technological, economic, and political barriers that make Mars colonization such a monumental undertaking. I'll leave a link to that video in the description. Now let's consider the terrain itself. Mars might not have active plate tectonics, but it has some of the most extreme topography in the solar system. Olympus Mons, the largest volcano we know of anywhere, rises about 72,000 feet, that's 22 kilometers, above the surrounding plains. It's nearly 2.5 times the height of Mount Everest. The Valles Marineris Canyon system stretches over 2,500 miles long and reaches depths of 4 miles in some places. That's about 4 times deeper than the Grand Canyon. This extreme terrain creates localized weather patterns, affects dust distribution, and poses navigation challenges. If you're trying to establish multiple habitats or explore the planet, you can't just drive wherever you want. You need to carefully plan routes around obstacles, some of which are continent-sized. Getting stuck or having a vehicle break down far from base could be a death sentence. The Martian surface is also covered with rocks of all sizes, from pebbles to boulders. These aren't smooth, weathered rocks like you'd find on Earth's beaches. They're sharp, angular, created by impacts and volcanic activity, then left unchanged for millions of years because Mars doesn't have the erosion processes that round off edges here on Earth. These rocks are hazards for rovers, for habitat construction, and for anyone attempting to walk around on the surface. Then there's the issue of Martian gravity, or rather the lack thereof. Mars has only about 38% of Earth's gravity. That's more than the Moon's 16%. But it's still significantly less than what our bodies evolved to handle. You might think lower gravity would make everything easier, but the reality is more complicated. In the short term, lower gravity feels liberating. You can jump higher, lift heavier objects, and move with less effort. But over weeks and months, your body starts to adapt in ways that aren't healthy. Your bones begin to lose density because they're not bearing as much weight. Your muscles atrophy because they don't have to work as hard. Your cardiovascular system becomes less efficient because your heart doesn't have to pump as hard against gravity. Astronauts on the International Space Station, which is in microgravity, experience these effects and have to exercise for several hours every single day just to minimize bone and muscle loss. Even with rigorous exercise regimens, astronauts still come back weaker. On Mars, with its partial gravity, you'd have similar problems, though potentially not quite as severe. But here's the question nobody can answer yet. Would exercise in Martian gravity be enough to maintain bone and muscle health? Or would settlers experience irreversible changes that would make returning to Earth's gravity impossible? There's also the issue of pregnancy and child development in low gravity, which brings up profoundly important questions if we're talking about true colonization rather than just temporary visits. No human has ever been conceived, gestated, or born in anything other than Earth's gravity. We have zero data on whether human reproduction would even be possible on Mars, and if it is, whether the developing fetus would grow normally. Studies on pregnant rats in microgravity have shown developmental abnormalities in the offspring. Their inner ear structures, which control balance, developed differently. Their muscle and bone formation was impaired. Now, Mars has more gravity than the orbital environment where these experiments took place, but it's still only about a third of what evolution has prepared us for. Would a child born on Mars have weaker bones that could never support Earth gravity? Would their hearts develop properly? Would their cognitive function be affected? These aren't just academic questions, they're fundamental concerns about whether humans can truly become a multi-planetary species. Let's shift our focus to something that might seem mundane, but is actually crucial: food production. We've already talked about the problems with Martian soil, but growing food on Mars involves so many more challenges that it deserves its own discussion. Plants need several things to survive: light, water, nutrients, the right temperature, and a proper atmosphere. On Mars, you're starting with none of these in the right quantities or combinations. Inside a pressurized greenhouse, you'd need to provide artificial lighting or maximize the weak Martian sunlight coming through transparent panels. But those panels would need to be radiation shielded, which blocks light, or unshielded, which exposes your plants to damaging radiation. You'd need to maintain temperatures between 50 and 85 degrees Fahrenheit for most crops, requiring constant heating in an environment where it's usually 100 degrees below zero outside. You'd need to maintain the right atmospheric composition, not just oxygen and carbon dioxide levels, but also humidity. Plants transpire, releasing water vapor, and managing that humidity in a closed system is tricky. Too much moisture leads to fungal growth and condensation that could damage equipment. Too little, and plants dry out. You'd also need to circulate air to prevent dead zones where carbon dioxide or oxygen accumulates. Then there's pollination. On Earth, wind and insects do this job naturally. On Mars, in your sealed greenhouse, you'd need to either manually pollinate every plant or find mechanical solutions. Imagine the time investment required to hand-pollinate enough crops to feed even a small crew. It's labor-intensive and requires expertise. The nutritional requirements for keeping humans healthy add another layer of complexity. You can't just grow potatoes, despite what the Martian suggested. You need a diverse diet to get all essential vitamins, minerals, proteins, and fats. That means growing multiple crop varieties, each with its own specific requirements. Some crops, like wheat and rice, take months to mature. If something goes wrong with a harvest, you're not just disappointed, you're facing potential starvation. And let's be honest about the energy requirements. Growing food indoors with artificial light is incredibly energy intensive. LED grow lights have improved efficiency, but you'd still need enormous amounts of power to produce enough food for a crew. Every kilowatt hour spent on food production is power that's not available for life support, water processing, or other critical systems. It's a constant balancing act with very thin margins for error. Now, here's something that really showcases how interconnected and fragile a Mars colony would be: the waste management and resource recycling challenge. On Earth, if your plumbing breaks, it's inconvenient. On Mars, it could cascade into a life-threatening crisis. Everything must be recycled because resupply from Earth takes anywhere from 6 to 9 months, costs millions of dollars per kilogram, and isn't guaranteed. Water recycling is perhaps the most critical system. The International Space Station recycles about 93% of its water, including urine, sweat, and even humidity from the air. A Mars habitat would need to be even more efficient, but water recycling systems are complex, require maintenance, and need replacement parts. Filters clog, pumps fail, and pipes can leak. If your water recycling efficiency drops from 93% to 85%, you might think that's still pretty good. But over time, that loss compounds, and you'd eventually run out of water unless you can extract and purify more from Martian sources, which we've already established is difficult and energy intensive. Waste management goes beyond just water. Human waste contains valuable nutrients that could be used for growing plants, but it also contains pathogens that need to be eliminated. The composting processes we use on Earth rely on specific bacteria and conditions that you'd need to carefully manage on Mars. Air recycling is equally crucial. You'd need systems to remove carbon dioxide that humans exhale and generate oxygen, either through mechanical means or possibly with photosynthetic organisms like algae. Each of these systems adds weight, complexity, and potential failure points. Redundancy is essential, which means doubling up on critical equipment, but that adds even more weight and cost. The engineering challenge is to create systems that are reliable, maintainable with limited spare parts, and simple enough that a crew with diverse expertise, but not infinite specialization, can repair them when they inevitably break down. Speaking of things breaking down, let's talk about the dust problem in more detail, because it truly is one of Mars's most insidious hazards. We mentioned earlier that dust storms can last for months and cover the entire planet. But even during calm periods, there's always dust in the air. The finest particles can remain suspended in the thin atmosphere almost indefinitely. This omnipresent dust would infiltrate every seal, coating and scratching every surface. The dust particles are rich in iron oxide, which is essentially rust, but they also contain silicates, which are similar to the quartz particles that cause silicosis in Earth miners. Breathing Martian dust would be extremely dangerous. Even with filters and airlocks, some dust would inevitably make it inside habitats over time. The electrostatic properties of Martian dust make it cling to everything. Experiments have shown that it's harder to clean off than lunar dust, which was already a notorious problem for Apollo astronauts. The dust would coat solar panels, reducing power generation gradually but persistently. It would scratch helmet visors, compromising visibility. It would get into joints and seals of spacesuits, causing wear and potential failures. Managing dust contamination would be a daily, exhausting, never-ending task. Furthermore, the dust affects visibility. Even without a major storm, atmospheric dust scatters light, creating a haze that reduces how far you can see. During a dust storm, visibility can drop to near zero. Imagine trying to navigate back to your habitat in those conditions. GPS doesn't exist on Mars yet. You'd be relying on inertial navigation, radio beacons, and landmarks you can't see. Getting lost in a dust storm would be terrifyingly easy, and once you're lost, your life expectancy is measured in hours as your suit's resources deplete. Let's consider the spacesuits themselves, because they deserve special attention. A Martian spacesuit would need to do far more than the suits used for spacewalks or moon landings. It would need to provide pressure, oxygen, temperature control, radiation shielding, communication equipment, and waste management, all while being flexible enough to allow work and durable enough to withstand the sharp rocks and abrasive dust. Current spacesuit technology isn't really up to the task for long-duration Mars surface operations. The suits used on the International Space Station are bulky, difficult to move in, and require significant effort to operate. They're also expensive to maintain and can only withstand a limited number of uses before components need replacement. For Mars, you'd need suits that astronauts could wear for hours at a time, multiple times per week, for years potentially. The pressure differential is particularly problematic. To maintain enough internal pressure for humans to function normally, about 14.7 pounds per square inch, like Earth's sea level pressure, would make the suit extremely rigid and difficult to move in. That's why most spacesuit designs use lower internal pressures, around 4 to 8 pounds per square inch, which requires pre-breathing pure oxygen to prevent decompression sickness. This pre-breathing can take hours and severely limits how quickly someone can respond to an emergency. Some engineers are working on mechanical counter-pressure suits that apply pressure directly to the skin through tight elastic garments, rather than using gas pressure. These would be much more flexible and wouldn't have the pre-breathing requirement. However, the technology is still experimental, and creating a suit that applies even pressure across every contour of the human body while still being practical to put on and take off, is extraordinarily difficult. Then there's the question of suit maintenance and repair. Spacesuits are complex pieces of equipment with hundreds of components. Something will eventually break, tear, or wear out. You can't just send a damaged suit back to Earth for repair. The crew would need the expertise, tools, and spare parts to maintain their suits on Mars. A critical suit failure during an EVA, that's extravehicular activity, could be fatal within minutes. Now let's talk about something that connects to the very core of what makes Mars so brutal: the planet's magnetic field, or rather, its absence. Earth has a strong global magnetic field, generated by the churning of molten iron in its outer core. This magnetic field extends far into space, creating the magnetosphere, which deflects most of the solar wind and cosmic rays that stream toward our planet. Mars lost its global magnetic field about 4 billion years ago when its core cooled and solidified. Without this protective shield, the solar wind gradually stripped away most of Mars's atmosphere over hundreds of millions of years. This is why Mars has such a thin atmosphere today and why the surface is bombarded with radiation. The InSight mission confirmed through seismic data that Mars's core is indeed liquid, but it's not generating a magnetic field, possibly because it lacks the convective processes that drive Earth's dynamo. Some regions of Mars's crust retain localized magnetic fields, remnants from when the planet had a global field. These crustal magnetic anomalies are strongest in the southern highlands and can be hundreds of times stronger than Earth's magnetic field locally, but they're patchy and don't provide planet-wide protection. NASA's MAVEN mission, which stands for Mars Atmosphere and Volatile Evolution, has been studying how the solar wind interacts with Mars's upper atmosphere since 2014. MAVEN's observations have been eye-opening. During solar storms, when the sun releases massive bursts of energetic particles, the rate of atmospheric loss from Mars increases dramatically. The spacecraft has measured ions being stripped away and accelerated into space by the solar wind's magnetic field. In fact, recent findings from 2026 revealed something called the Swan-Wolf effect occurring in Mars's atmosphere for the first time. This phenomenon, where charged particles are squeezed along magnetic flux tubes, had only been observed in Earth's magnetosphere before. This discovery tells us that Mars's interaction with the solar wind is even more complex and dynamic than we previously understood. The solar wind essentially compresses and shapes what little magnetic environment Mars has, creating temporary structures that channel particles in unpredictable ways. For anyone on the surface, this means that radiation exposure isn't constant. It spikes during solar events, and those spikes can be severe. A major solar flare or coronal mass ejection directed at Mars could deliver a lethal dose of radiation to unprotected astronauts in just a few hours. On Earth, we're warned about these events by satellites monitoring the Sun, and our magnetosphere protects us anyway. On Mars, you'd have warning from orbiting spacecraft, but your only protection would be to get underground or into heavily shielded shelters immediately. If you're out on an EVA when a solar storm hits, you might not make it back in time. The cumulative radiation exposure over a long-term stay on Mars is genuinely concerning. Scientists have calculated that a 500-day mission on the Martian surface would expose astronauts to approximately 100 millisieverts of radiation from galactic cosmic rays alone, not counting solar particle events. For comparison, the annual exposure limit for radiation workers on Earth is 50 millisieverts. Astronauts on Mars would exceed career limits within a couple of years. The biological effects of this radiation are still being studied, but we know it increases cancer risk significantly. It can cause cataracts, damage the cardiovascular system, and potentially affect the brain. Some studies using particle accelerators to simulate space radiation have shown that it causes inflammation in brain tissue and might accelerate the development of Alzheimer's-like symptoms. The astronauts who venture to Mars might return as heroes, but they'd also return with health consequences that could shorten their lives. Now, let's consider the communication challenges that make Mars feel even more isolating. Because Mars and Earth are both orbiting the Sun at different speeds and distances, the communication delay varies depending on where both planets are in their orbits. At the closest approach, when Mars and Earth are on the same side of the Sun, the light travel time is about 4 minutes one way. At the farthest, when they're on opposite sides of the Sun, it can be up to 24 minutes one way. This means a simple back-and-forth exchange could take anywhere from 8 to 48 minutes. You can't have a conversation, you can't ask for immediate advice when something goes wrong. Every interaction becomes an exchange of detailed messages with long pauses in between. For emergency situations, this delay could be the difference between life and death. The crew would need to be trained to handle any conceivable problem independently, because waiting for instructions from Earth simply isn't viable. Moreover, during certain times in the Martian year, Mars passes behind the Sun from Earth's perspective, a period called solar conjunction. During these weeks, which happen roughly every 26 months, communication becomes unreliable or impossible because the Sun's corona interferes with radio signals. Mission planners have to account for these blackout periods, ensuring that spacecraft and habitats can operate autonomously when needed. The psychological impact of this communication barrier cannot be overstated. Humans are social creatures. We evolved in communities where communication was immediate and constant. Being millions of miles from everyone you've ever known, unable to have a real-time conversation with anyone except your handful of crewmates would be psychologically crushing for many people. Video messages from family would arrive minutes or hours after being sent, creating an emotional distance that compounds the physical one. Studies in extreme isolation environments on Earth have shown that even with modern communication technology, people experience profound loneliness and depression. The third quarter phenomenon is well documented in Antarctic research stations and submarines, where morale tends to hit its lowest point around 3/4 of the way through a long deployment. On a multi-year Mars mission, this psychological crisis could happen far from any possibility of evacuation or relief. Let's discuss the actual journey to Mars, because the brutality begins long before you ever set foot on the red planet. A trip to Mars takes roughly 6 to 9 months depending on the orbital positions and the trajectory chosen. That's half a year or more confined to a spacecraft with a small crew living in microgravity, exposed to radiation without even Mars's thin atmosphere for partial protection. The spacecraft would need to be large enough to carry everything required for the journey and the surface stay. Life support systems, food, water, spare parts, scientific equipment, and habitat components. The more mass you send, the more fuel you need, which adds more mass, which requires more fuel. A problem called the tyranny of the rocket equation. Current estimates suggest a crewed Mars mission would require a spacecraft weighing several hundred tons in low Earth orbit. During the voyage, astronauts would experience the health effects of microgravity we discussed earlier. Bone loss, muscle atrophy, fluid shifts that affect vision, and immune system suppression. They'd be living in close quarters with the same few people for months, unable to step outside, unable to get fresh air or see a horizon. The psychological strain would be immense even before reaching Mars. Radiation exposure during the transit is also a major concern. In deep space, beyond Earth's magnetosphere, cosmic rays and solar radiation are intense. The spacecraft would need shielding, but shielding is heavy. There's been discussion of using water or fuel as shielding, surrounding the crew compartment with tanks that serve double duty for protection and storage. Some designs propose using the ship's waste and supplies as makeshift shielding. But even with these measures, astronauts would still receive significant radiation doses during transit. And then there's the landing itself, which is arguably one of the most dangerous phases of the entire mission. Mars has enough atmosphere to cause heating during entry, but not enough to slow a spacecraft adequately using parachutes alone. This creates what engineers call the 7 minutes of terror, though for a crewed mission it would be even more terrifying because the spacecraft would be much heavier than any robotic lander we've sent before. Current entry, descent, and landing systems used for rovers like Curiosity and Perseverance work for payloads of about 1 ton. A crewed mission would need to land perhaps 20 to 40 tons of equipment and habitat modules. The physics becomes exponentially more difficult. You'd need a combination of heat shields, supersonic parachutes, and powerful retro-rockets firing in the thin Martian atmosphere. Any failure in this complex sequence would be catastrophic, with no possibility of rescue. Once on the surface, assuming you survive the landing, the work immediately begins. You can't just walk out and start exploring. First, you'd need to deploy and activate your habitat systems. Solar panels or nuclear reactors need to be set up and connected. Life support systems need to be tested and brought online. Supplies need to be unloaded and organized. All of this happens while you're living in the cramped landing vehicle, conserving resources, hoping nothing goes wrong during setup. The first EVAs, those extravehicular activities, would be focused purely on survival infrastructure rather than science or exploration. You'd be working in a spacesuit, in an environment we've already established is trying to kill you, doing complex technical work where mistakes could be fatal. The pressure to get everything right the first time would be enormous because there are no do-overs, no second chances if a critical system fails during deployment. Let's talk about something that often gets overlooked in discussions about Mars colonization. The return journey. Getting to Mars is hard, but leaving Mars might actually be harder. To launch from the Martian surface back into orbit, you need a rocket and fuel. That fuel is incredibly heavy, and bringing it all from Earth would be impractical. This is why mission designers talk about in-situ resource utilization, or ISRU, which means making fuel on Mars from local resources. The most promising approach involves taking hydrogen from Earth and combining it with carbon dioxide from the Martian atmosphere to create methane and oxygen through a process called the Sabatier reaction. This sounds straightforward in theory, but in practice, it requires complex chemical processing equipment, significant power and time. You'd need to run this fuel production facility for months or even years before you have enough propellant to launch. What if the fuel production system breaks down? What if it doesn't produce fuel at the expected rate? What if there's contamination that makes the fuel unusable? Every one of these scenarios could trap astronauts on Mars indefinitely. The returned vehicle becomes a symbol of hope sitting on the surface, but it's useless without fuel. The psychological weight of knowing your only way home depends on machinery functioning flawlessly in one of the harshest environments imaginable would be crushing. Even if everything works perfectly and you generate the fuel, you still face the challenge of launching from Mars. The rocket needs to work perfectly despite sitting on the Martian surface for potentially 2 years, exposed to dust, temperature extremes, and radiation. Rocket engines are precision instruments with thousands of components that all need to function in perfect sequence. A single stuck valve, a single clogged fuel line, a single failed sensor could doom the mission. And once you've launched successfully, you face another 6 to 9 months in space for the return journey. during which you're even weaker from your time in Mars's low gravity. Your radiation exposure is even higher, and your psychological reserves are depleted from the stress of the surface stay. You need to time your departure to coincide with a favorable orbital window, which only occurs every 26 months. Miss that window and you're waiting another 2 years. Now, let's explore the environmental hazards we haven't fully covered yet. Mars has landslides and avalanches, particularly along crater walls and in the polar regions where seasonal carbon dioxide ice sublimates and destabilizes slopes. The Mars Reconnaissance Orbiter has captured images of massive avalanches in action, with clouds of dust and debris cascading down kilometer-high cliffs. If your habitat is built near any sort of slope, you'd need to carefully assess the geological stability. There are also features called recurring slope lineae, dark streaks, that appear seasonally on slopes in warm regions. Scientists initially thought these might be caused by flowing water, which would have been exciting for astrobiology. More recent research suggests they're more likely caused by flowing sand or some other dry process, but their exact nature is still debated. Regardless of what causes them, they represent ongoing surface changes that colonists would need to understand and account for. Mars also has its own version of quicksand in some regions. Fine dust accumulated in certain areas can have almost no cohesion, creating pockets where equipment or even people could sink. Without the water content that characterizes Earth quicksand, this Martian version might actually be more dangerous because there's no buoyancy to help you float. If you break through a dust crust into one of these pockets, you could be in serious trouble. The planet's geology also includes lava tubes, which are actually one of the few features that could work in favor of colonization. These are underground tunnels formed by ancient lava flows, and they could provide natural shelter from radiation and temperature extremes. Radar data from orbiters suggests that some Martian lava tubes could be enormous, potentially hundreds of meters wide and kilometers long. These could theoretically house entire colonies if they're structurally sound and accessible. However, exploring and utilizing lava tubes brings its own dangers. They could be unstable, with ceiling collapses waiting to happen. They might contain hazards we can't detect from orbit, like chasms or toxic gas pockets. Cave-ins on Earth can trap people with tons of rock. On Mars, a cave-in would likely be a death sentence with no possibility of rescue. Any underground habitat would need extensive geological surveying and engineering to ensure stability. Let's shift our attention to the search for life on Mars, because this connects to some unique hazards. NASA's Perseverance rover is currently collecting samples that will eventually be returned to Earth by a future mission. One of the primary goals is to search for signs of ancient microbial life. But what if Mars still has life, perhaps deep underground where liquid water might exist? This raises the issue of planetary protection, which works both ways. We don't want to contaminate Mars with Earth microbes, which could compromise the search for Martian life and potentially harm any native ecosystem. But we also need to consider the reverse. What if Martian life, should it exist, is hazardous to humans? This sounds like science fiction, but it's a legitimate concern that astrobiologists take seriously. Any Martian life would have evolved completely independently from Earth life. It might have different biochemistry, different proteins, different metabolic processes. Our immune systems would have no experience with Martian microbes, and Martian microbes would have no experience with human biochemistry. The results of contact could be unpredictable. Most scientists think the risk is low, but low risk isn't no risk, especially when you're talking about the health of astronauts far from any advanced medical care. This is why sample return missions from Mars involve multiple layers of containment. When Martian samples eventually come back to Earth, They'll be handled with extreme caution in biosafety facilities. Astronauts on Mars would need to follow similar protocols, treating Martian material as potentially hazardous until proven otherwise. This adds complexity to every operation, from soil collection for agriculture to the simple act of entering and exiting habitats. Medical care on Mars deserves its own discussion because it represents one of the most daunting challenges of long-duration missions. On Earth, if you have a medical emergency, you can usually reach advanced care within hours. On the International Space Station, a critically ill or injured astronaut can be evacuated to Earth within a day if necessary. On Mars, evacuation isn't an option. The crew's medic is the most advanced care available, and they'd need to handle everything from routine illnesses to major trauma to potential surgical emergencies. The range of medical equipment and supplies you can bring is limited by mass and volume constraints. You can't pack an entire hospital. Difficult decisions have to be made about what medical capabilities to include. Dental problems, for instance, might seem minor, but an abscessed tooth can become life-threatening if it leads to sepsis. The crew would need a member trained in basic dentistry, along with the tools to perform procedures like extractions if necessary. Surgical capabilities are even more challenging. What if someone develops appendicitis, a kidney stone, or suffers a severe injury? Performing surgery in Mars's low gravity, with limited equipment and supplies, would be extraordinarily difficult. The risk of infection would be high. Recovery would be complicated by the radiation exposure and the generally stressful environment. Some injuries or illnesses that are survivable on Earth with prompt treatment could easily be fatal on Mars. Mental health care is equally critical and perhaps even more difficult to address. We've touched on the psychological challenges, but the reality is that depression, anxiety, severe stress reaction, and even psychosis could occur during a Mars mission. On Earth, treatment might involve therapy, medication, and environmental changes. On Mars, your treatment options are extremely limited. The crew would need someone trained in psychological support, but they'd be facing their own psychological challenges while trying to help others. Medication supplies would be limited and would degrade over time, especially under radiation exposure. Recent studies have shown that pharmaceuticals stored on the International Space Station lose potency faster than they do on Earth, likely due to radiation. On Mars, with higher radiation levels and longer mission durations, this problem would be worse. Drugs might become ineffective or even harmful as their chemical composition changes. This means a limited formulary that becomes even more limited as time passes. There's also the issue of medical privacy and autonomy in such a small group. If you're struggling mentally, everyone around you will know. There's no private space, no ability to take a mental health day away from your crewmates. The social dynamics become incredibly delicate when everyone depends on everyone else for survival, but also needs space to cope with their own challenges. Conflicts that would be minor annoyances on Earth can escalate into mission-threatening crises when there's no escape. Let's talk about something that really emphasizes the interconnected fragility of Mars habitats: fire. Fire is one of the most dangerous emergencies possible in a sealed environment. On the International Space Station, fire protocols are extensive because a fire in microgravity behaves differently than on Earth and could quickly consume the limited oxygen supply while producing toxic fumes with nowhere to go. On Mars, fire would behave more like it does on Earth because of the gravity, but it would still be catastrophic in a sealed habitat. The atmosphere inside would be oxygen-rich to support human life, making fires burn intensely. Smoke and toxic combustion products would accumulate rapidly in the enclosed space. Water for firefighting is precious and limited. Venting the atmosphere to extinguish the fire means losing your breathable air, And while you might be able to generate more oxygen, that takes time and energy. Fire suppression systems add weight and complexity to the habitat design. Detection systems need to be reliable but not overly sensitive, because false alarms that trigger suppression systems could cause more damage than they prevent. The crew would need extensive fire safety training and regular drills, but even with perfect preparation, a fire could destroy critical equipment or force evacuation to backup shelters, creating a cascade of problems. Electrical fires would be particularly concerning because they could damage the very systems needed to respond to the emergency. If a fire takes out your power distribution system or communications, you're suddenly dealing with multiple simultaneous failures. This is why redundancy is so critical, but also so expensive in terms of mass, volume, and complexity. Every backup system is another thing that can break and needs maintenance. Now let's consider the long-term viability question that hangs over any discussion of Mars colonization. Can a settlement ever become truly self-sufficient, or will it always be dependent on Earth? The answer to this question determines whether we're talking about a scientific outpost that requires constant resupply or actual colonization, where people can live permanently and sustainably. Self-sufficiency requires manufacturing capability. You need to be able to make spare parts, tools, and eventually complex electronics from local materials. Mars has the raw elements you'd need: iron, silicon, aluminum, carbon, but extracting and processing them into usable forms requires industrial infrastructure. You need mining equipment, smelters, fabrication facilities, all operating in the harsh Martian environment. 3D printing technology has been proposed as part of the solution. The idea is that you could print replacement parts and even structural components using Martian regolith as feedstock. NASA has experimented with this concept, even sending a 3D printer to the International Space Station. But the reality is that current additive manufacturing can't produce everything you need. High-strength alloys, precision electronics, advanced polymers, these require specialized manufacturing processes that are difficult to replicate on Mars with limited resources. There's also the knowledge and expertise problem. A small colony can't have specialists in every field. People would need to be cross-trained in multiple disciplines, but there's a limit to how much expertise one person can maintain. Complex repairs might require knowledge that nobody in the colony possesses. This is where communication with Earth becomes crucial. But we've already discussed the time lag that makes real-time consultation impossible. The economic model for Mars colonization is another massive question mark. What does Mars have that would justify the enormous cost of transport to and from Earth? The planet doesn't have rare elements that are uncommon here. There's no obvious resource worth the expense of interplanetary shipping. Some have suggested that Mars could become a center for research and innovation, but that's more of a philosophical argument than an economic one. Tourism has been proposed, and while there might eventually be a market for wealthy individuals willing to pay for the experience, the infrastructure required to support tourism safely would need to already exist, which means someone else would need to foot the bill for initial colonization. Government funding is the most likely source, framing Mars as a scientific and inspirational endeavor rather than a profit-generating one. At least initially, the timescales involved in Mars colonization are sobering. Even with aggressive development, we're talking about decades to establish a small, fragile outpost, and potentially centuries before anything resembling a self-sufficient city could exist. The commitment required spans generations. Political support and funding would need to remain consistent through changes in administration, economic cycles, and competing priorities. History suggests this kind of sustained commitment is rare. Let's examine some of the specific technologies that would need to work flawlessly for a Mars colony to survive. Water extraction and purification systems are absolutely critical. We've talked about subsurface ice, but actually accessing it means drilling or excavating through frozen ground at temperatures well below zero. The equipment needs to operate reliably in extreme cold, which is challenging because materials become brittle, lubricants freeze, and batteries lose capacity. Once you've extracted ice, you need to melt it, which requires significant energy. Then it needs to be purified because Martian ice likely contains dissolved salts, perchlorates, and other contaminants. Purification isn't a one-time process. It needs to happen continuously as you extract more water. The filtration systems will accumulate contaminants and need cleaning or replacement. Every step in this chain is a potential failure point. Oxygen generation is another critical system. The Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, which flew on Perseverance, has successfully demonstrated that oxygen can be produced from Martian carbon dioxide. This is a remarkable achievement that proves the concept works. However, MOXIE is a small experimental device. Scaling it up to produce enough oxygen for human consumption, pressurizing habitats, and creating rocket fuel is a massive engineering challenge. The process requires high temperatures, around 800 degrees Celsius, to split carbon dioxide into oxygen and carbon monoxide. Maintaining these temperatures continuously while keeping the equipment from degrading requires advanced materials and significant power. The carbon monoxide produced is toxic and needs to be either safely vented or used for other chemical processes. Any leak or malfunction could poison the habitat atmosphere or waste precious resources. Food production technology would need to be incredibly reliable and efficient. Hydroponic or aeroponic systems that grow plants without soil are promising because they use less water than traditional farming and allow precise control of nutrients. However, they're also complex systems with pumps, sensors, and nutrient delivery mechanisms that can fail. Algae and cyanobacteria have been proposed as compact, efficient food sources that could grow in closed-loop systems, but humans can't survive on algae alone, and making it palatable enough for long-term consumption is its own challenge. There's also been research into cellular agriculture, growing meat from cell cultures rather than raising animals. This could provide protein without the massive resource requirements of livestock. However, the technology is still in its infancy on Earth, and adapting it to work reliably in a Martian habitat with limited resources would require significant advancement. Each of these food production methods comes with trade-offs between efficiency, reliability, nutrition, and palatability. The computing and communication infrastructure on Mars would face unique challenges. Electronics are sensitive to radiation, which can cause single-event upsets where a cosmic ray flips a bit in memory or corrupts data. Spacecraft use radiation-hardened electronics, but these are expensive, heavy, and typically less powerful than commercial components. A Mars colony would need a balance between protection and capability. Data storage is also affected by radiation and extreme temperatures. Hard drives with moving parts could fail in the dust. Solid-state drives degrade over time, especially under radiation. Maintaining backups of critical data, software, and knowledge bases would be essential, but that requires redundant storage systems that all need power and maintenance. Losing data could mean losing the knowledge needed to repair critical systems, creating a potentially fatal spiral. Communication satellites in Mars orbit would be necessary for global coverage and relay to Earth. These satellites would need to be maintained or replaced eventually, which means the colony would need launch capability, not just for returning to Earth, but also for accessing Mars orbit. This adds yet another layer of technological infrastructure that needs to exist for long-term survival, let's discuss the construction challenges that would face any Mars colony. Building on Mars is fundamentally different from building on Earth, and not just because of the environmental conditions. The materials available are different, the forces and stresses structures experience are different, and the consequences of failure are immediately catastrophic rather than merely inconvenient. Martian concrete is a concept that's been extensively researched. You can't just use Earth-style concrete because it requires water, and water is far too precious on Mars to mix into building materials. Scientists have developed alternatives using Martian regolith mixed with sulfur or other binding agents that can be melted and cast into structural elements. Some proposals involve using the perchlorates in Martian soil as a binding agent, which would turn a toxic hazard into a useful resource. However, testing these materials on Earth under simulated Martian conditions is not the same as using them on Mars itself. The long-term durability under constant temperature cycling, radiation exposure, and the corrosive properties of Martian dust is unknown. A building that seems structurally sound initially might develop microscopic cracks that grow over time, eventually leading to catastrophic failure. With pressurized habitats, structural failure means rapid decompression and death for anyone inside. Construction equipment would need to be specially designed for Martian conditions. Hydraulic systems might not work properly because fluids behave differently at low pressure and temperature. Electric motors and batteries perform poorly in extreme cold. Dust infiltration would be a constant battle, with abrasive particles wearing down moving parts faster than they would on Earth. Each piece of equipment represents a massive investment in transport cost and would need to last for years or decades with limited spare parts. The actual process of building is complicated by the need for spacesuits. Construction workers on Earth can perform delicate tasks with bare hands and can work long shifts. On Mars, you're limited by your spacesuit's life support duration, typically around 8 hours maximum, and you're working with thick gloves that limit dexterity. Complex assembly tasks that might take hours on Earth could take days or weeks on Mars. The frustration of trying to thread a bolt or make a precise connection while wearing pressurized gloves in freezing temperatures would be immense. There's also the question of habitat design. Do you build on the surface with radiation shielding, or do you build underground? Surface habitats have the advantage of natural light and potentially better views, which might be important for psychological health. But they're exposed to radiation, temperature extremes, and dust storms. They also present a larger target for micrometeorites, which are more common on Mars than Earth because there's almost no atmosphere to burn them up. Underground habitats offer better protection from radiation and temperature swings, and they could potentially use natural lava tubes as we discussed earlier. However, excavation is energy-intensive and dangerous. You'd need to ensure geological stability and deal with potential groundwater or ice that could destabilize structures. Underground facilities also feel more confined and isolating, potentially worsening psychological challenges. The lack of natural light would require artificial lighting that mimics day-night cycles, adding to power requirements. A hybrid approach, partially underground with protected surface extensions, might offer the best compromise, but it's also the most complex to build. Every design choice involves trade-offs between safety, psychology, resource efficiency, and construction difficulty. There's no perfect solution, only less bad options that might work well enough to keep people alive. Let's talk about something that might seem minor, but would actually be a significant quality of life issue: laundry and clothing. On Earth, we take clean clothes for granted. On the International Space Station, there's no laundry facility. Astronauts wear clothes until they're too dirty, then dispose of them in cargo vehicles that burn up in Earth's atmosphere. New clothes arrive on resupply missions. On Mars, you can't afford to constantly dispose of clothing and wait for new shipments. But washing clothes requires water, detergent, and energy. A traditional washing machine uses dozens of liters of water per load. Even highly efficient designs would still need significant water that would then need to be reclaimed and purified, adding to the recycling system's burden. Drying clothes in the low pressure and thin atmosphere of Mars would be challenging. Evaporation works differently, and a tumble dryer would require precious energy. Some proposals suggest developing clothes that can be worn for extended periods without washing, perhaps using antimicrobial fabrics or self-cleaning materials. But these technologies are still largely experimental, and even the best fabrics would eventually need cleaning. The alternative is accepting that hygiene standards on Mars would be significantly lower than on Earth, which has its own psychological and health implications. Personal hygiene in general would be challenging. Water for showers would be strictly rationed. Quick sponge baths might be the norm, with full showers being a rare luxury. Wastewater from washing would need to be captured and recycled. The International Space Station has a toilet system that uses vacuum suction and separates liquid and solid waste for recycling, but it's notoriously difficult to use and frequently breaks down. A Mars habitat would need more reliable sanitation systems, but they'd still be far less comfortable than what we're used to on Earth. Psychological adaptations to reduced hygiene, limited privacy, and constant resource conservation would be necessary. These might seem like small quality-of-life issues compared to radiation and life support failures, but they compound over time. The cumulative stress of daily discomforts, combined with isolation and danger, creates psychological burdens that can break even well-trained individuals. Now let's examine the legal and governance questions surrounding Mars colonization. Current space law is based primarily on the Outer Space Treaty of 1967, which states that celestial bodies cannot be claimed by any nation and must be used for peaceful purposes. However, the treaty is vague on many practical questions. Can private entities claim Martian land? Who has jurisdiction over a Mars colony? What laws apply to crimes committed on Mars? If someone commits a serious crime on Mars, perhaps a violent act or sabotage that endangers the colony, who prosecutes them? The colony would be too small and resource-constrained to operate a prison. Sending them back to Earth for trial takes years and costs millions. Exile isn't an option because they die. The social compact that keeps order on Earth through the threat of legal consequences doesn't translate easily to a small isolated community where survival depends on everyone cooperating. There's also the question of decision-making authority. In the early stages, a Mars colony would likely operate under a hierarchical command structure similar to military or naval operations, with a mission commander having final authority. But as the colony grows and potentially becomes more permanent, would residents demand democratic governance? How do you balance individual rights with collective survival when one person's actions could kill everyone? Resource allocation would be a constant source of potential conflict. Who decides how limited water, power, and food are distributed? What happens if someone uses more than their share? In a scarcity environment, every decision about resources is potentially life or death. The social systems that manage resource distribution on Earth, markets, governments, charity, all assume a baseline level of abundance that simply doesn't exist on Mars. There are also questions about reproduction and children's rights. Should people be allowed to have children on Mars, given the unknown health risks and the harsh environment those children would face? If a child is born on Mars and later wants to emigrate to Earth, Could they even survive in Earth's higher gravity if they've spent their entire developmental period in Mars's lower gravity? These aren't just hypothetical questions, they're ethical dilemmas that would need answers before any long-term colonization effort. The concept of a Martian identity might emerge over time. People born on Mars, or who have spent most of their lives there, might develop cultural perspectives and priorities different from Earth. They might resent Earth's oversight or resource control. The history of colonization on Earth shows that colonies often eventually seek independence from their founding nations. Would Mars eventually demand autonomy? Could it even survive as an independent entity, or would it always be dependent on Earth for survival? Let's shift focus to something more immediate, the timeline and mission architecture of early Mars expeditions. NASA's current plans involve the Artemis program returning humans to the Moon first, using it as a testing ground for technologies and procedures that would later be used on Mars. The Lunar Gateway, a space station in orbit around the Moon, would serve as a staging point. This Moon-to-Mars approach makes sense from a risk management perspective, but it also adds decades to the timeline. Private companies, particularly SpaceX, have proposed more aggressive timelines. Elon Musk has famously stated ambitions to send humans to Mars as early as the 2030s, though these dates have shifted repeatedly. SpaceX's Starship, currently in development, is designed to be a fully reusable super heavy launch vehicle capable of carrying large payloads to Mars. If successful, it could dramatically reduce launch costs and make more ambitious missions feasible. However, the technical challenges of Starship are immense. The vehicle needs to successfully launch, refuel in orbit through multiple tanker flights, survive the months-long journey to Mars, land safely on the Martian surface with enough fuel remaining for the return journey or after local fuel production, and then successfully launch from Mars and return to Earth. Each of these steps is monumentally difficult, and all of them need to work reliably before you can risk human lives. The mission architecture also needs to account for redundancy and abort options. If something goes wrong during the journey to Mars, can the crew abort and return to Earth? The orbital mechanics make this difficult or impossible during certain phases of the trip. Once you've committed to the trajectory, you're going to Mars whether you want to or not. Similarly, if something goes wrong on the surface, the crew needs backup habitats, life support systems, and contingency plans. Every backup adds mass and cost. Cargo missions would need to precede crewed missions, pre-positioning supplies, habitats, fuel production equipment, and return vehicles. This means multiple successful cargo landings at the same site on Mars before humans arrive. If any of those cargo missions fail, it could delay the crewed mission by years, waiting for the next favorable launch window. The logistical complexity of coordinating multiple missions across years is staggering.